I guess a bunch of transfer functions to deal with multi-input, multi-output systems. Okay, so we had a couple of these. Let me go back here.
Like how do you get the dimension of IP? Because you said it's like in this example, because IP is 2 by 2, we have it in this form by 4 by 4 because it's single input. So how do you understand what's the dimension?
IP is going to be, if you have a 2-input system, IP will be
2 by 2.
2 by 2. If IP is a 3-input system, then IP will be 3 by 3.
So how do you understand it from transfer matrix? How do you understand how many?
Right. And so I believe that a transfer matrix is going to be P by Q. I think I will have to think about that for a second. But I think that's absolutely correct. Yes, yeah, so I should probably put that over here. Anything else? Okay, so we want to talk a little bit about stability. So given the output of a system due to any input, this is your convolution integral. This would be of a causal LTI system. So linear time invariant causal system. Systems course that the convolution integral is commutative. So if I convolve A with B, it's the same as convolving B with A. Okay, so I'm going to take the absolute value of that output. That is going to be less than tornado warning in this area until 4:30. I think we're in the safest place on earth right here, so I think we're okay. Okay, so so I can claim that if I take the absolute value of the convolution integral, it's going to be less than or equal to the absolute value of each of my individual functions and integrate it over. Okay, this is sort of like the triangular inequality that, is that the one I'm looking for? That if it's not what I'm looking for. If I sum up, if I sum up two vectors, take this vector plus that vector, I get this third one, and that third one is going to be less than or equal to the lengths of the first two. It's kind of a similar concept here, right? So if I integrate this over all time, and then take the absolute value, it's going to be less than, let's just say less than, even though it's less than or equal to. If I force this thing to be positive, and force this thing to be positive, and then integrate over all time, because I could have some positive and negative influences over here. If I force them all to be positive, then they're going to add, what's the word I'm looking for? Not negative, they're going to add positively, I guess. So this is a pretty easy statement to make. So if I do that, then I'm just going to put some upper bound on here, on my input. Okay, so now I've forced myself to have a limited input. So now this thing, we're going to say okay, so now I've got my output is limited to, or has a limited input. It's going to be then less than that limited input plus this integral. I'm going to define that integral to be less than infinity, and then finally you have Okay, so if I limit my input, so I don't have any crazy infinite inputs, and this thing holds true, then my output will be limited in some way, shape, or form, okay? So this is what defines a stable system in terms of a bounded input, bounded output, right? All right, so now let's look at slightly different. Okay, this is the Laplace transform of my system's input impulse response. Okay, so I'm just going to define a certain transfer function, a g of s, as a single pole placed somewhere, okay? I know from my Laplace transform table that that gives me an impulse response of that. Okay, so the question is, where does P1 have to be in order for that to hold true? Okay, this is an exponential, right? You know what exponentials look like? They either go kind of like that, or kind of like that. This is where anybody remember this? Okay, so in order for this integral, if I want to integrate over all time an exponential, well, this one's obviously going to blow up to infinity. This one will give me a constant value, okay? So all my poles have to fall on the left-hand side of the S-plane. So if I was going to look at a pole zero plot, my pole is going to be that side, right? That gives me decaying exponentials, which then therefore gives me a stable system. Okay, so if we go to the state space representation of LTI systems, we've got this time domain representation, and then we take the loss transform, we get that representation. And then I can go ahead and solve for x of s, and then I can put that x of s into the output equation. And I get that. I missed the b somewhere. And then if I divide by my input u, then I get my transfer function g, or transfer matrix g. Okay, so in this regard, remember my A, B, C, and D matrices are just numbers. For an LTI system, they don't vary over time. So the only place where I want to get poles in my system is right here. Right?
Excuse me,
Yes, sir.
I just got a message from my wife. All the students in Catering Lab, they,
Basement?
yeah,
Yeah, I got an email, so.
All right. They say all students, or can
Yeah,
the
all
teachers
students.
come
yeah.
too? Flash flood warning. So go to the basement? I mean, that's fine. I mean, if you got the message, let's go.
I got the tornado warning message too.
The email.
I don't think this building's gonna blow over.
I got the email.
And I get an email about the engineering students.
Tornado warning from Randy. Please seek shelter at lowest level of building or interior room with no windows immediately. I say let's go to the basement. Come on, let's go.
People running around all day. Yeah, just pull up something, they'll get semi.
Come on. Take your stuff or don't take your stuff, you just gotta move.